These videos are offered on a pay-what-you-like basis. You can pay for the use of the videos at my website. There's a link to my website in the annotation. The address is www.freelance-teacher.com/videos.htm. Or you can just use the link in the annotation. Thank you. Let's say that we wanted to calculate the area enclosed here. What would be a function we could write down for this area?
A equals x times y.
Excellent. And let's say we wanted something that measured the total length of the line that I've drawn. What would be the expression for the length of that line?
X plus y plus y.
Okay. And then what does that simplify to?
2x plus 2y.
Okay. So let's say we call this side here x. What might we call this?
Y.
Good. Or if you wanted to, you could call this the width, w for width, and this h for height. Now, I put a dashed line here. How could you calculate the total area that's enclosed inside the solid and the dashed line?
X times y.
Same as before. How would you calculate the total length that's represented by the solid line? Not including the dashed line.
It's just x plus 2y.
That's right. All right. That's not super hard, but that's some of the types of thought processes we have to go through in this section. If we're not including the dashed line in the length would be x plus 2y. Good. What might be a good name for this distance? A good symbol.
X.
And how about for here?
Y.
Great. Or if you wanted to, you could call this w for width and this h for height, whichever you feel more comfortable with. Good. So let's write down an expression for the total area that's enclosed.
X times y.
Yeah, I think that's all there is to it. And now let's write down an expression for the total length of all the lines. How would you figure out the total length of all the line segments?
It's 2x plus 3y.
Okay, excellent. That's right. 2 x's, but 3 y's. Notice that this little line here in the center didn't have any effect on the area. This little line in the center had no effect on the area, but it did change the total length of all the line segments. And I think that you worked that out correctly here. Okay, good. Now let's say I'm going to make a box with a square bottom. First of all, do you see how that's different from what we were doing before? What we were dealing before with were squares and rectangles, which are two-dimensional. But a box is three-dimensional. So this is going to be different because a box is three-dimensional, not two-dimensional. So I get to practice the old drawing skills here. Let's see. You might want to kind of study how I drew this box because you might need to draw some three-dimensional structures here. On this section. Okay, so what we're going to do is we're going to draw a box with a square bottom. A box with a square bottom. So what might be a good symbol for this distance?
Box with a square bottom. Oh, we could use w.
That's fine. What would then be a good symbol for this distance?
That's also w.
And this distance?
H.
Excellent. Outstanding. So the important thing is that you didn't make up a new variable here. How did you know that this was also w?
Because it's a square bottom.
That's right. There was that hidden piece of information. Good. So we want to use different symbols for things that are different, but the same symbol for things that are the same. So these both are the same. All right, so now let's write down a formula for the volume of the box.
Okay, so you can just write h times w, or h times w squared.
Perfect. Now let's write down a formula for the total surface area of the box.
So we have a square on 1, 2, 1. Okay, so it's w squared plus the sides. So 1, 2, 3, 4. 4wh plus actually it's 2w squared, because I guess the top and the bottom are the same size. I guess. Can you assume that? Or is it proven in the drawing?
Well, if they say it's a box, it's normally assumed that all the sides are perpendicular to each other. So we're assuming, yes, so we're assuming that the sides are perpendicular to the base, which would mean that the top has to be the same size at the bottom. So yeah, I suppose it would be possible to have a box with different sizes at the top and the bottom, but you're not going to see that probably in your course. So yeah, it wasn't specifically stated, but generally when they say a box, they do mean a symmetrical box. That's a good point.
Okay.
So what would be your answer?
2w squared plus 4wh.
Excellent. Okay, that was a very good process. That's good the way that you thought through each of the steps there. You saw that there's the top and the bottom, 2w squared, and then the four sides around the edge. Excellent. Now we're going to draw an open box with a square bottom.
Okay.
I'm getting a little sloppy with my drawing here. Okay, so notice this picture looks identical to the last picture. How is this box? The pictures look the same, but how is this box different from the previous box? What does it mean that it's open?
It has no top.
No top. That's right. Open means I don't know how to draw no top,
Right.
but you just need to realize this is just air here.
Okay.
I can't really draw it differently, but we want to make sure that we see that it's no top. That's what it means that it's open. So now, how would you calculate the volume of the box?
The volume of the box is...
Oh, so first of all, we need to give
the
some
same.
names. So what would be a good name for this?
Can use w.
And for this?
Square bottom, w.
We know we can use the same symbol because, again, we said it had a square bottom, so those sides are the same. I didn't really draw it like a square, but that's what I was going for. And then what would be this?
H.
Can we assume that this is W?
No,
No.
we can't.
Because they didn't. That would be a cube, by the way. If
right.
all three sides were the same, that would be a cube. But they didn't say it was a cube, just a box. Is it possible that this side is the same as the others? Yeah, it's possible, but we can't assume that. Okay, it's possible this is a cube, but we can't assume it's a cube. So now we can write the expression for the volume.
Okay, so the volume is just h times w squared.
Excellent. Good. Notice you can't write the formula until you name the characters. First, you have to make up variables for the key elements, and then you can write down the formula. That's an important part of optimization problems. First, you write down the letters. First, you have to assign letters to the key variables, and then you can write down the formula. All right, and now let's write down an expression for the total surface area.
Total surface area is, it's w squared plus 4 HW. So it's similar to the before, but we don't have a top, so it's just 1W squared.
Okay, excellent. So notice the volume was the same as before. The volume was the same as before, but there's less surface area because there's no top. There's less surface area because there's no top, and you work that out correctly. Okay, excellent. Okay, try this on your screen.
That.
Outstanding, perfect. So before you could take the derivative, you had to use the distributive rule and get rid of the parentheses. Before you could take the derivative, you had to use the distributive rule and get rid of the parentheses. Excellent, that was very good. I'll go back to my screen. Let's try this problem.
Okay, so take the derivative of this expression. So
By the way, that was supposed to be a 2, not a z.
okay.
If it's a z, I would put that little cross in it. So are you using the product rule?
Mm-hmm.
Okay, yeah, you totally could use the product rule here, but I don't think that would be the best approach in this section. So let's erase that and see if there's another approach. What's another way you can simplify what's inside those parentheses before you take the derivative?
That.
Yeah, absolutely. That's good.
Yeah.
That uses some of the techniques we were going over before. Good. Now, you might want to simplify. So do you know how to take that derivative? What now?
Quotient rule?
You could use the quotient rule, but I think that would be more complicated than we need. Maybe I'll go to my screen and show how to finish this off. All right, first of all, here's how we could rewrite the first step to make it clear that it's legal. Remember that it's best to go with baby steps. So we turn them both into fractions, and then we can see that we're multiplying. So would you agree with this?
Mm-hmm.
And then this?
Yeah.
Now we can use what we've seen before, the constant multiple rule. When there's a constant times a function, you can just take the constant out of the derivative. When there's a constant times a function, you can just take the constant out of the derivative. So we should pause here, take a look at these steps to see how we did this, because this comes up a lot in this section.
Okay.
So now what? What can I write now? You might be getting a little confused, but now we can just take the derivative.
Okay. So 3 minus a.
3 minus 2a, right?
Oh boy. Yeah, 2a.
Okay. Seems like you're probably getting a little tired. So that's the technique that we would use here on this problem. So now we figured out this derivative. So the derivative we were trying to find was this one. Okay. All right, there's a lot of derivatives like that in this section, so I think it's important to see how to do this. If we use other approaches, we're going to get expressions that are too complicated to work with. So I think that we really have to take this type of derivative. Because in a lot of these problems, we're going to have to take the derivative twice in a row. And if we don't simplify things, the derivative is going to get horribly complicated. So take another look at this and see if you can follow how we went through each of these steps.
Okay, so we started with a times a fraction. And then we just made it 1, 3a minus a squared over 2. And we try to take the derivative. But fortunately, it will take too long. So take out 1/2. And then we could use product rule, but that would take too long.
So what we used was the constant multiple rule. When you have a constant times something else, when you have a constant times a function, you can just take the constant out of the derivative and just take the derivative of the function. That's an important rule in this section. Do you see how that applies here? Okay.
Yeah.
All right, and then do you see how we did the end of the problem?
1/2. So constant multiple rule. And then 3 minus 2a.
That was just taking the derivative.
Mm-hmm.
One thing that might be throwing off your intuition here is I'm not using x like we normally do, I'm using a. But I'm doing that on purpose because in this section, oftentimes we're not going to be using x's. We're going to be using new made-up variables, right? So we have to get used to taking derivatives with respect to other variables, not just x. Okay? Let's try this on your screen.
Like that?
Okay, good. Now there was one point there where you were on the verge of making a mistake and then you caught yourself. So point to the step where you were using the constant multiple rule. Yeah, actually used it in the previous step, that one here. For a moment there, you were taking the derivative of the constant. But that's not the way the rule works, because after all, what is the derivative of a constant?
Zero.
And that would have zeroed out the whole thing. So when we use this rule, we just take the constant out of the derivative. We don't take the derivative of the constant. So anyway, you did catch yourself, and you did that correctly. And then you went and used the distributive rule. That was good. Now it turns out in this section that it'll be better not to use the distributive rule in the last step. What you did was correct, but it turns out in this section that last step is not going to be helpful to us. Let's go ahead and erase that very last step where you did the 4/3 minus 2/3 d, and we'll just leave the answer as you had before. What you wrote down there was correct, but this will be a better approach for us. Okay, so that ended up giving us this as our answer. Let's take a look. So third, and then you took the 1/3 out. Okay, good. All right, so I'll go back to my screen. Okay, so we went over some of the geometry that we're going to need for this section, and now we're going over some of the calculus that's coming up in these sections. These are the types of derivatives that we need to take. And in this section, we have to use these approaches rather than like the product rule or the quotient rule, because after we take the derivative, we're going to have to do algebra on our answer. And if the answer comes out to be horribly complicated, we're not going to be able to do the algebra. And also, we're going to have to take the second derivative. And if our first derivative is horribly complicated, we're not going to be able to take the second derivative. So in this section, we really do need to use these approaches for derivatives. There are some other longer approaches you could use, but they're not really going to help us to get the problems right. So this is some important techniques here that we're using. Basically, our goal here is almost all these problems can kind of be simplified down to polynomials. We're trying to get the expression down to kind of a polynomial and then take the derivative of the polynomial, not say a fraction. We're trying to, it's kind of similar to what we were working on before. That was one reason why we were spending some time on fractions before. We need to get rid of the fractions here and rewrite this as a polynomial. And then we can take the derivative and continue with that. And remember, here's the constant multiple rule. Remember, for a second there, you were making a mistake and you were treating it as if it was like this. For a second, you were treating it as if we were taking the derivative of the constant. But actually, we just take the constant outside of the derivative, and we just take the derivative of the function. Okay, all right. Well, that's our time. That's our time for today. If you wanted to meet tomorrow, we could continue to work on this section and try doing some of the sample problems. Did you want to schedule for tomorrow?
Yep, and just one quick question about that problem. So is it possible to take 4/3 out and then find the derivative of d minus d squared?
I lost the problem. 1 second.
Oh,
here it is. Okay, I'm sorry. So I'm sorry, say again?
So instead of going this way...
You're on your screen? Okay, good.
Yeah,
Let me take a look.
Sorry. Could I go this? 4/3 times 1 minus 2d. 4/3 minus...
Okay, well, you tell me. So back up, point your cursor to the next expression.
Mm-hmm.
No, the next expression in this new approach. So down below.
Okay.
Good. Now you're asking me whether that is legal or not. You tell me. How can you check whether that's legal?
I can multiply. I can distribute 4/3, and I should get the same answer.
So check that and see if you get the same thing.
Yep.
Keep going. Keep writing down what you get to make sure it's the same thing.
Well, I guess I have subtraction issues. I'll have to clear it up on my own time. But yeah, this isn't right, I guess.
Yeah, so you don't need to erase it. That's a good thing to check. So what's on the bottom of that fraction? Okay, so you can see it doesn't quite, oh, okay, maybe you're not quite sure how to subtract fractions? Okay, yeah, so sometimes when there's some gaps in some of the pre-calculus material, that can make it difficult to these problems. The answer is when you subtract fractions with the same denominator, the denominator doesn't change. It should be the same denominator in all of them. But that's not really the key issue. You can already see it's wrong anyway because notice you have too many 4s on the top.
Okay. Yeah.
Right? So you may as well have this correct in your notes. So you can rewrite the 3 denominator off to the left. Okay, so you can still see that it came out incorrectly because you have too many 4s there. So you can always, basically what you tried to do is you tried to factor out a 4/3, right?
Mm-hmm.
Well, you can always check if you factored correctly by trying to use the distributive rule. Okay, so it turned out that was not legal. That was not something that we were able to do. I think I'll go back to my screen and finish up. So let's see. In this case, we got 4d minus d squared over 3. So basically, here's what you were asking. You were asking whether you could go from here to here, except you kind of skipped the step. Again, one of the best pieces of advice I can give you is try to take smaller steps in your algebra, tiny little baby steps. So first, we were trying to factor out the 4/3, but we can see that this is not right because if you multiplied this out, you would get a 4 in front of both terms. Mm-hmm. But there is no 4 over here. So what you were just trying here would have worked if you had this. The trick you just were trying would have worked if there was a 4 in front of both terms, then you could factor out the 4 from both terms. But you don't have a 4 in front of both terms, so you can't do that factoring. Does this 4 refer to both terms on the top?
No.
No. So you can't factor it out. Does this 3 refer to both terms on the top.
Yep.
So that is the thing you can factor out. So here was the correct way that we did. This is very important. We really need this for this section of the test. This is correct. The 3 does refer to both things on top, so that's the thing that we can factor out. Now, if your fraction subtraction skills are a little weak, this is tricky because it would be tough to check this, but this is the legal thing that we can do. We can factor out the 3 because the 3 really was referring to both of those terms. And now we can use the constant multiple rule.
Okay.
Now we take, so before you use the constant multiple rule, make sure that you can actually factor out the constant. This is what I mean by taking tiny little baby steps. And now what goes in this parenthesis?
4 minus 2d.
And now you could use the distributive rule, but it turns out that in this section it would be better just to leave it the way it is. So here we have our answer. Okay, so there is so one reason why we were spending so much time on those algebra issues before for L'Hopital's rule is they come up in other sections. So some of those algebra issues are kind of coming up here as well. We're going to need this kind of algebra in order to solve these problems as well. Okay, so anyway, that took us to here. So that's our time for today. I tried to go over some stuff that's going to be crucial for this new section. So this would be the stuff that's especially important. We talked about these situations here that come up, and then we started going over some derivatives that we're going to need to take in this section. So these last couple of problems are certainly very important to review to try to get comfortable with how to do these types of problems. Okay, so let's talk about how we could simplify this function. This is something we were talking about yesterday. So this is something that's been giving us some trouble going over some of the algebra that we need for this section. So there's no magic bullet for this, but I would still give you the same advice as before, which is try to break things down into very small baby steps where you can understand where each baby step works. And then if you do it that way, you can be confident that you're doing the algebra correctly. What most people do instead of that is they just kind of try to memorize a pattern of what is legal and what isn't. But that's not very effective if you don't understand why the patterns are working, because then you can't adapt them to any other type of situation, and it's hard to remember them as well. So how could I break this down in baby steps? Well, here's one step that I think we talked about yesterday. Do you see why this step is legal?
Mm-hmm.
And then for our next little small baby step, do you see how this is legal? Oops, yeah. I guess I should actually write it like this.
Yeah.
Do you see how this is legal? Okay, yes. So now I'd have to put this in parentheses, and now we could rewrite it like this. Now, what if you're still not sure whether this is legal? Well, you could do the distributive law and make sure you could get back to where you started here. Okay, so that's some important algebra that is going to be useful to us. How could I re-express this?
Can rewrite that as AC over BD.
That's right. When you're multiplying fractions, you just multiply the numerators and you multiply the denominators. Now here's something that gave us a little trouble yesterday, adding two fractions. This is a different process. First of all, you can only add fractions if they have the same denominator. So in this case, I already set it up so that they already have the same denominator. So in this case, you only add the top, and the denominator stays the same as before. And this should also make common sense to you. So for example, if you have a quarter of a pizza and someone gives you another quarter of a pizza, doesn't that mean you have 2 quarters of a pizza? Yeah. So this rule actually kind of makes sense if you look at a numerical example as well. One thing that gives people trouble is maybe some people know how to add fractions when they're numbers, but they lose their intuition when there's variables. But it's the same rule in both cases. Now the rule for subtraction is pretty similar to the rule for addition. So what do you think the answer would be here? How could we re-express this?
You can just rewrite it as a minus b over e.
Okay, that's right. So if you start with 2 quarter slices of pizza and some mean person takes away one of your quarter slices, you have 1/4 slice left. So that actually makes some good sense if you plug in some actual numbers. Okay, so so these are some algebra skills that might be helpful to us to checking our work as we go along. Let's say that we're trying to do this derivative. Let's say we're trying to work out this derivative. How could we approach this? Well, one thing you could use, you could do the distributive law and distribute the 3/8 over these 3 terms. And that would work, but then that would give you a bunch of fractions running around in the expression. So there's a simpler approach here. Instead of distributing the 3/8 in this case, because this is a constant that's multiplied times the rest of the formula, we can simply take the 3/8 completely out of the derivative. Now, what do I have left to do? Do I still have to take the derivative of the 3/8? Well, no. You don't have to take the derivative of the constant in this rule. Do I still have to take the derivative of this expression? Well, yeah, this expression I still have to put a prime on. So notice there's no prime here, but I still have to put a prime here. So this rule that we just used here, this is the constant multiple rule.
Okay.
When there's a constant that is being multiplied times an expression, you can simply take that constant completely out of the derivative without taking its derivative. And then you just take the derivative of what's left. And that'll give us some simplifications as we go along. And now the rest of this derivative should be easy for us to work through. Okay, good.
And I think you can prove the constant multiple rule by actually using the product rule, and one side is zeroed out. So then you just have the other side.
That's an excellent point. Yes. So that's an excellent point. You could prove this rule by using the product rule. So another way of what you're saying is that in a way this is not necessary. You could just use the product rule here. But that really introduces a very unnecessary level of complication. It gives us more chances to make mistakes and get confused. So I think it's much better to use the constant multiple rule. But that's still a very good point. It's good to see that this really is a consequence or a special case of the product rule. That's right. That would be a pretty easy proof. Okay, so let's go on to this. Okay, so try doing this derivative on your screen.
Okay. So we can use constant multiple rule. We can pull out. And then well, I think maybe we do have to use product rule here because we have this other variable.
Okay, I'll go back to my screen and give you some help with that. And again, my most important piece of advice to you here is take small, tiny little baby steps. So the first thing that we could do here, we need to simplify this expression somewhat. The first thing I would do is rewrite it like this, a tiny little baby step. so that I can combine these into a single fraction. So now what would go on the top of the fraction?
G8 minus G squared over 3.
That's right. Do you see how this is certainly improvement? This is much simpler than this expression that we had here, and we did it with tiny little baby steps so we could be confident that each step was correct. Now the next thing we can do is the algebra technique that we were talking about before. Basically, we're factoring out a 1/3. This is basically a factoring technique. We could check that this was legal by multiplying these and seeing that we could get back to where we started here. And it should be clear that this is a very small little step and this is also legal. And now, at this point, we can use the constant multiple rule and take the 1/3 out.
Okay.
And on the right-hand side of this equation, I should keep writing ditto to show that it's the same the left-hand side is the same expression as before. G, this expression here. Okay. And now it should be easy to take that derivative. And now I'm pretty much done, so I'll rewrite what the left-hand side stands for. Okay, now you could now use the distributive rule and distribute the 1/3 across, but it will turn out in this section that this is the more convenient way to leave the derivative. It'll be more convenient to leave it like this. Okay, so this gave us some trouble again. So the key thing here is before we can really use the constant multiple rule here, we had to combine these into a single fraction. Before we could use the constant multiple rule, it was important to combine these into a single fraction. I think one thing you were considering was using the product rule. You could use the product rule here, but ultimately that's really going to be a not very good way to do the problems in this section. So basically all of the functions in this section can be reduced ultimately to a constant times a polynomial. That's going to be our goal. Okay. Pretty much all of the functions that we're going to be dealing with in this section, we're going to be able to reduce it to this form, a constant, oftentimes a fraction, times a polynomial, and then it should be very easy to take the derivative using the constant multiple rule and the rule for polynomials. So that's basically our goal with each of these expressions I'm giving you. The goal is re-express this so it looks like this. Re-express this so it looks like a constant times a polynomial, and then we can use simple rules to take the derivative. So that's the key idea, so I'll just say that one more time. Pretty much all the functions we're going to be dealing with in this section, we're going to be able, our goal is going to be to re-express them as a constant times a polynomial, and then it should be straightforward to take their derivative. Okay. Let's try this problem on your screen.
Okay.
Okay, good. So that was similar to the ones we were doing before. The key thing is to remember that in this section, we're generally going to be able to rewrite the function. Our goal is to rewrite the function as a polynomial times a constant, oftentimes a polynomial times a fractional constant. And then it should be easy to use the constant multiple rule and derivative rules to take the derivative. Let's point to the third line of your solution. Point to the third line. Great. I think we should put in one more set of parentheses there to show that the 1/5 is multiplying times the 2h minus h squared.
Okay. Yeah.
But you did that correctly. Okay, good. I'll go back to my screen. This is a 6. Forget it. It's a 7. All right. Let's try this on your screen.
Okay.
And remember, our goal for each of these problems in this section is to try to get the expression as written as a polynomial or a polynomial times a constant, and then take the derivative.
Okay. Well, we already have our constant. So just rewrite this. Okay.
Okay, you could use the distributive rule here, but in this section, we may as well just leave it like this. Very good. So again, we got this written as a polynomial, or a constant times a polynomial. Point to your first line of your solution on the right-hand side. Great. I noticed there that you rewrote the a as a over 1. But if you think about it, it's not really helpful here to rewrite it as a over 1. You may as well just leave it as a.
Okay.
So we can erase that over 1. What made you do that? Well, why did we do that on previous problems? When is that useful? Well, if you have one expression that's a fraction and another expression that's not a fraction, it can help to make them both into fractions by putting one term over 1. But in this case, we already started with no fractions. In this term, nobody was a fraction. And we should be happy about that. We should be happy there's no fractions and there's no need to start inserting them. So that putting it over 1 trick is helpful when you have one thing that's a fraction and one thing that isn't. But if nobody's a fraction in the first place, then it's not necessary for us to introduce fractions. Okay, so that wasn't necessary, but that didn't mess you up. You still ended up with the correct answer. That's good. I'll go back to my screen.
Okay.
Okay, so let's try to take this derivative. And again, as usual, our goal is to, before taking the derivative, we want to rewrite this as a polynomial, or as a polynomial times a constant. And then we can take the derivative.
Okay. So we have polynomial. So
Okay, so we had some trouble with that previous line. Let's go back to the previous line. It looks like you tried to use the distributive law there. Is that what you were thinking, using the distributive law?
Yep.
Okay. However, you can't apply the distributive law to a parenthesis that has a square on it, if you see what I'm saying. That the 2 minus 3x is squared, you can't distribute the x over that as long as there's that square. We have to get rid of the square first. We have to get rid of the square first. So let's erase the line that we're working on now. So the first thing you need to do is expand the 2 minus 3x squared. So what does 2 minus 3x squared mean? We can rewrite it as 2 minus 3x times 2 minus 3x. Okay, and now we need to just keep using FOIL and multiplying until we've got a polynomial.
Okay. Outer, negative 6x. Inner. Slash.
Okay, that's a good use of parentheses and brackets. Good.
Negative 6. Negative 6x minus 6x. Okay, so now we can distribute. So we have 4x Okay.
Okay, good. Notice how in each of these expressions we are ultimately able to get to the point where we just have a polynomial. And those are easy to take the derivative of, or a polynomial times a constant. In this case, we didn't even have the constant. We just reduced it down to a polynomial. So I think that's generally going to be the case for pretty much all of the functions you deal with in this section. Your goal, you're going to be able to get it down to just a simple polynomial like this, and then it'll be easy to take the first and second derivatives. Since we're going to have to take two derivatives, it's important to have a pretty simple expression. If you use something like the product rule for the first derivative, the second derivative can start to get more complicated as well. Okay, good. So that gives us that expression. I'll go back to my screen. So can we apply the distributive rule in this situation?
No, we can't.
Yeah.
We have to
This is
FOIL,
wrong.
reverse FOIL first.
This would be wrong. You can only apply the distributive law over parentheses that don't have any exponents on them. So how do we get rid of this exponent? Well, you were just mentioning you can get rid of the exponent by using FOIL to multiply y plus z times y plus z. Okay?
Mm-hmm.
Let's try this problem.
So we have to. Nine minus 6x. Nine minus 6x. Okay.
Okay, good. Notice how much simpler it was to take the derivative of your next to last expression than it would have been of the first expression. We really, if you were trying to take the derivative of that first expression, you need the product rule and the chain rule. But by doing some algebra, we got it to just look like a normal polynomial, which is easy to take the derivative of. And that's generally what we're going to be able to do in this section. Okay, that was a good process. I'll go back to my screen. Okay, let's try this on your screen. And remember that our goal again, this looks more complicated and more scary than the previous examples, but our goal again is to keep doing little algebra steps until we've got this looking just like an ordinary polynomial, or a polynomial times a constant.
Make sure with this. Here, can I check your screen one more?
Sure.
Okay. Okay.
It's always important to know you're doing the right problem. Good.
Okay. So they want to either get a polynomial or a constant and polynomial. So. I think we can just Okay.
Okay, this was a trickier problem than we'd done before, but I think you worked that out. Whoops. I think you worked that out correctly. Good. So let's go back to the start and review those steps. Okay, let's point to the third line from the bottom of your screen. Good. That line should have an extra set of parentheses to show the 1/2 is multiplying times that expression. Good. So the key thing that you did here was canceled out the x on the bottom, and you did this one little step at a time to make sure that each step was legal. And you ended with 3 times negative 3 x squared. Okay, one moment. Okay, that was a good process. This was harder than the ones we did before, so it's good that you took your time and did small steps and worked it out. Let's look at one of the steps that you had done there. So one of the steps that you did was at this point, it might have been safer here before we cancel to prove that we can cancel by factoring out the x here.
Okay. Okay.
Because sometimes people think they can cancel when they really can't. Now it's clear we can cancel. Okay, so I'm not saying this is absolutely mandatory, but I think sometimes we have trouble knowing when we can cancel and when we can't. So I think this is a slightly safer approach. You can cancel when you can factor out the term that you're canceling and write the expression like this. So what you did is you went straight from here to here. You did that correctly, you didn't make any mistakes, but maybe at this point, since we're not confident about our algebra, it might be better to include this extra step. All right, but overall, that was a good process for working out this problem. That was a trickier problem than the ones that we did before, and you took your time and you worked it out. Notice, notice how much easier it is to take the derivative of this expression than it would have been of this expression. To take the derivative of this expression, first you'd have to use the product rule, then you'd have to use the quotient rule. So it'd kind of be a big mess. It really is better to know the algebra for working this out. Let's go back to your screen one more time. And let's look at your answer. Okay, yeah, I just wanted to double check that that was correct, and it is 1/2 times negative 3 minus x squared. Excellent. Okay, I'll go back to my screen. Let's try this problem.
Okay. So 2x. Okay, so 4x squared and x squared. X squared. Negative 2x. Oh. Yeah, negative 2x minus negative 2x. 4x plus 1 plus negative 4x plus 4. Negative 4x plus negative 4x. 8x. Okay.
Let's see. Okay, good. You may as well remove the brackets from that last line.
Okay.
We were putting the brackets in there to help us take the derivative, but now we've taken the derivative. The brackets aren't wrong, but we don't need them. So if we hadn't used the algebra approach here, we would have had to use the chain rule 2 separate times. So this is a superior approach. And notice that the function really did simplify quite a bit as we went along. Okay, that was a good step-by-step process. That was a good process for that problem. I'll go back to my screen. Tell me when you have this problem written down.
Yep.
Okay, we're going to work on this problem together, but why don't you take 30 seconds just to kind of think about the problem and visualize this and think about how you'll attack it, and then we'll go through it together.
Okay, so Joe has 1,200 feet. That's once the fence off. A rectangular field that borders the straight river. So I'm going to draw a straight river on my paper. And then I'm going to draw a rectangle that has one side that borders the river. So what dimensions for the fence would give the field the largest area? Okay, so I'm going to write down that the side that's across the river is x, and then the two sides that are perpendicular are y.
Okay, so I was going to do this on my screen, but you know you're off to such a great start. Why don't we do it on your screen? So
Okay.
go ahead and transfer that work so far to your screen. And if you get stuck, I'll give you some help, but that's an excellent start.
Okay. So area equals x times y. Then our relationship is that we have 1,200 feet of fencing. So we have x plus 2y equals 1,200. And so we need to pick a variable. So I'm going to pick solve for x so we don't get a fraction. Okay, cool. So now we can
do it like this. Okay, so now we can say that okay, cool. So now we can set okay, so I think y is maybe 300. We don't know yet. So now I can find x by plugging in for y. So x equals 1200 minus okay, so now we can prove this by just a second. It's negative, so it's concave down. And so the question said, what dimensions for the fence would give the field the largest area? So 300 feet. And if we add these up, 6, 9, 12. Okay, cool.
Okay, well that's excellent. I think we got that right. That was a great process. Okay, that's excellent. So you had said you were having you said you were having a lot of trouble with these problems.
Yeah.
Maybe you've made some progress on them, or maybe this one was just too much of a softball for you. But this would be a fair question for the test. So we'll have to move on to some harder problems. But this would already be a fair question for the exam. So have you made some progress since then, or?
Yeah, I went to the library really early this morning to work on something else for another class, and I finished early, so I started working on this section.
Okay, well, obviously you made some good progress on that, so that's great. Excellent. Good. Okay, so that was a very good method. So let's summarize the steps here so we can apply them to the more difficult problems. So one thing you did here that was important is you made a picture. We always want to make a picture. And something else that you did was important is that you invented variables for the key quantities. The variables you invented were x, y, and a. So I think those were good intuitive variables that you invented. So picture, inventing variables. Then on these problems, we're generally going to have two different equations. So yeah, step one is the picture. Step two is invent necessary variables, names. Then you need to write down two equations. One equation we could call the constraint equation, and one we could call the goal equation. So you wrote down your constraint equation and your goal equation. So we need an equation for the constraint and an equation for the goal. So the constraint here was that x plus 2y had to equal 1,200, because we only had 1,200 feet of fencing. So that was the constraint. The goal was that we wanted to maximize the area. So a equals xy was our definition of our goal. We were trying to maximize a. Good. And then we can use, then you plugged in. So you got, remember that we only know how to work with functions of only one variable. So I guess after step 4, you usually have to solve the constraint for one of the variables and then substitute that into the goal so you only have one variable. So that's a little bit long to write out, but you know what you're doing here. You solve the constraint for one variable so you could substitute into the other equation so that you could have an equation with only one variable. So you got ay equals 1,200 minus 2y times y, and that's where you started using some of the algebra we talked about today. Before you took the derivative, you used the distributive rule so that you could get just a simple polynomial. And why did you take the derivative? Because we've learned that's the way to find maximums and minimums, right? We've learned that the way to find maximums and minimums is to find the critical number. So you did that. But we also know that critical numbers are not always maximums. They could be minimums, or they could be neither a maximum or a minimum. So you use the second derivative to prove that that was really a maximum. Okay, so those were all very excellent steps. I'll go back to my screen. Okay, so what else is there to say about this problem? One thing I might have done in the picture, I might have drawn the picture like this instead of drawing a line here, just to make it a little bit clearer that we don't need any fence along the river.
Okay.
Now, you obviously understood that because you put that into your constraint. In your constraint, you didn't include this line segment because you don't need any fence along the river, but this is the way to draw the picture to make that clearer to us. But the key thing is that you saw we don't need fence along the river because the river is bordering that side. It's a little bit interesting here to just kind of think about this without calculus. So one thing that you might try to do to get a very large area, one thing you might try to do is try to make x very large. So one thing the farmer could have done was put in a really large x. But you can see you don't want to overdo that, because if x is really large, y is going to be so small that you're still not covering much area. After all, if x was equal to 1200, y would have to be 0, and there would be no space there at all. So you don't want to make x too large. Something else that you might consider here is that you might instead make y really, really large. You might make y really large, but the problem with that is then x would have to be tiny. Well, again, that's not going to be the maximum, because obviously if you reduce x to 0, there's no volume here at all. So just kind of, it can be interesting to think about this intuitively first. Obviously, the answer has to be somewhere in the middle, not a huge x and not a huge y. What were the answers that you got?
600 for x and 300 for y. Yeah.
Good.
Yep.
Now, I don't think that's really obvious, right? I think like a naive student might have guessed that these numbers should be equal. But notice we didn't end up making them equal. So the answer here is not 100% obvious. You really do need the calculus to work it out. So this is one of the very first times in the whole course that when we actually saw what the heck calculus is good for.
Right.
So here's an actual practical problem that could arise in real life that you could actually use the calculus to solve to get a non-obvious answer. Something else I wanted to point out there was you got in this problem that a double prime was negative, right? And so you said that means that this is concave down, so we have a maximum. Now, in the past, what we said is if f prime of x is 0 and f double prime, let's call this c to call it a critical number, and f double prime of c is negative, that would tell us that we have a local max.
Okay.
But that's not quite good enough on this problem, because we don't want to find a local max, we want to find the absolute maximum. So we need a new rule that we haven't talked about before. The new rule is, it's very similar to the old rule. If f double prime of c is 0 and f double prime of x is negative for all x's in the domain, then you have an absolute max. And that really is should be kind of intuitive, because this would just mean that the function is concave down everywhere. Well, if the function is concave down everywhere, then it can only have one maximum, and that must be this point right here. So this is slightly different from our old rule. This is how we prove we have an absolute maximum. It's not good enough that f double prime is negative at the critical number. It has to be negative at all x's in the domain to have an absolute max. But I think on this problem, f double prime was like -4. And it was -4 everywhere. So that was how we knew we had an absolute max, because it didn't depend on x. It would be negative everywhere. Okay, very good. Okay, so let's move on. You understood how to do that, so let me give you a different type of problem. One moment.
So was that last problem from the website?
No, that problem was
Okay.
not from the website. But I still think that would be a fair problem for your instructor to put
Yeah,
on the
for sure.
test.
They look very similar.
Those fences along the river problems are pretty popular. Okay. All right. So here's the problem, and you can try working this out on your screen again. Obviously, this is a slightly different problem, but try to use the same general approach that you used on the last problem, because that was a good approach.
Okay. Okay. So 864. Box, square base. Okay. So, square base, find the dimensions that maximize the volume of the box. Okay, so you drew a picture, and now we need to label the size. The bottom equals square. Okay, this is x. This is x. So if it has to be y, or else it'll be a cube. Okay. So volume equals x times x. 2xy. Wait, no. X squared y. $64, let's get rid of the variable. Box with a square base. The base is sides of x. So the volume is x times y. Okay. So now we need to make a constraint. So we have 800. 64. And then we have the top and the bottom are the same. And the bottom surface area is x squared, x times x, so 2x squared. This is the bottom and top plus, what is this side? xy, 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 2xy, this is xy as well. So xy, 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 and xy. So we have 1, 2, 3, 4, 5, 6 sides. 1, 2, 3, 4, 5, 6. Okay. So we need to solve for one variable. So we can do this. Oh, oh. Move this over. That's one way. Is there an easier way? If we move this over, 864 minus 4xy.
So one thing you have to decide here is which variable is easier to solve for,
Right.
x or y. Well, I think it's pretty clear in this case that y is easier to solve for 2 reasons. It's easier to solve for y because how many copies of y were there in the original equation?
4.
Maybe that seemed like a weird question. What I meant is there was one copy of it, but there was 2 copies of x. My point is just that x appeared in 2 different terms and y appeared in only one term. So it was already closer to being solved for y than it was for x. More importantly, the x's were different. One was squared and one was not, whereas the y was not squared. So both of those things make it much easier to solve the equation for y than x. Both of those reasons, the equation is already closer to being solved for y than x. So your first instinct was a good one to solve for y.
Okay. All right, so we have this, and I guess we could.
You might think that the expression you have now, 864 minus 2x squared over 4x, is complicated, but it would have been even worse if we tried to solve for x.
Mm-hmm.
The only way to solve this for x would be to use the quadratic formula. So this is as simple as we can get.
Okay, so now I can move on. So I have x squared times 864 minus 2x squared over 4x. And this equals, well, okay, now I can x. Okay, cool. So I got my volume. And now I need to take the derivative. that. Now, I can set this equal to 0. Multiply both sides by 4. Yeah. So that's 12. Negative 12. This is talking about our side axis. So now we have x. And this is in so define y. Squared. 4 times 12. 864 minus 2 times 12 squared divided by 48 is 858. Can't be right. 864 minus 864 minus 12 squared is 144 times 2, 288. 864 minus 288 divided by 48. Yeah, that's not right. Okay. It's 12. Okay. So that would make this a cube. So I guess we can test maximizing the volume of second derivative. Second derivative is here. Okay. Messed up somewhere. Alright. So this, I feel like this part's good. So now I plugged it in here. This is y. Oh wait, no. Okay, now I see what I did. Yeah. Right. I plug in for y. That's what y is.
Okay, so if you thought about it some more, you might be able to figure out where we went wrong here, but to save time, I'll give you some help. Let's scroll down to the bottom. You just kind of lost your bearings at the end and forgot why you were taking the second derivative. You kind of mixed this up with another type of problem. So remember the purpose of taking, so we know that x equals 12 is a critical number. That means it could be a maximum, or it could be a minimum, or it could be neither. And now we want to apply the second derivative test to test whether it's a maximum or minimum or neither. And that's where we got confused. So do you remember, how do we use, what is the second derivative test? How do we use the second derivative test to test whether a critical number is a maximum, a minimum, or neither?
Right, so we take the derivative of the first derivative, and if it is positive, then we have a minimum, and if it's negative, we have a maximum.
So there really wasn't any need or reason to set the second derivative equal to 0. That's where you went wrong. Where you went wrong was where you were setting the second derivative equal to 0. That was something that we did on a different type of problem. That's useful when you want to find where the concavity changes. If you want to find the points where the concavity changes, you have to know where the second derivative is 0. But on this problem, we don't want to know where the second derivative is 0. We want to know what is the second derivative. Well, basically remember that to find an absolute maximum, we need to prove that the second derivative is negative everywhere on the domain. Well, what's the domain here? The key thing is that, as I think you already recognized, the x's have to be positive, right?
Right.
The x's have to be positive or they don't make sense. So the domain is positive x's. So when x is positive, is that derivative, is v double prime going to be positive or negative?
V double prime would be negative.
So all we have to do now is write that that is negative for all positive x's, for all x's in the domain. We can just write that that is negative for all x's in the domain.
Okay.
And that proves that that's a maximum. Okay, so that would be an important part to review. That's where we were getting confused. Other than that, that was a very good process. But we got a little confused at the end. You know, the fact is we've never really used the second derivative test much in this exact way. So I can see how we got a little confused at that point. Sorry, go ahead.
Sorry, it's... I guess the x was throwing me off. So I saw the x and I was like, well, I guess I have to get rid of, or I have to set the x equal to something, but that wasn't true.
So in a way, we do have to set it equal to something. Remember, what we have to check to find an absolute maximum, we have to make sure that the second derivative is negative for all x's in the domain. So you kind of have to ask, what would happen if I plug in any positive x? And you can see that if you plug in any positive x, the f double prime will always come out negative.
Okay.
Okay. Okay, so let's go back to the beginning and review the steps here. So you started by drawing a picture. That was good. And then you made up the variables x and y. That was good. We had to use y for the height because the problem didn't say this was a cube. So it was possible that the vertical was different. Now notice that doesn't mean it can't be a cube. It's possible. It's possible for x to equal y. We just need to be open to the possibility that they're not equal. It turned out that they really were equal, but we didn't force them to be equal. We proved that that was the best approach. You had a little trouble. So then you wrote down your constraint and your goal equations. That was good. And in the constraint equation, you always want to solve for whichever variable is easier to solve for. So remember, it should be clear that it's easier to solve for y than x here, largely because the y isn't being squared in the equation. So that's going to make it easier to, it's easier to square a variable that's, solve for a variable that doesn't, and then y only appears one time. So sometimes you have to use your judgment to decide which variable is easier to solve for. And if solving for one variable doesn't work, maybe you just have to try the other variable. Okay. You got two answers, 12 and negative 12. But then you realize that negative 12 isn't really in the domain here because we need only positive x's make sense since they're supposed to be lengths. So you threw out one of the answers. So that was a good approach. Good. I'll go back to my screen.
Okay.
So the units here were inches. So what would be, if we were going to measure the area, what would be the units for area?
An area would just, it's just...
what would be the units for area?
It's just inches squared.
That's right. And what would be the units for volume?
Inches cubed.
And what would be the units for length?
Inches.
Good. What does what did X and Y stand for? Length, area, or volume?
X and Y are the lengths of the sides.
Good. So what should be their units?
Inches.
But I think you were writing down square inches.
Yeah.
I don't know how picky your instructor would be about that, but if I was the grader, I would take off a point for that. All right, so it's important to put down the right units. So the units are not square inches. Why did you write down square inches? Well, there was area in the problem, but X and Y did not refer to areas. So these are the correct units to put in our answers. Good. Let's see. So what was the function that we were that you ended up with here? You ended up with v equals. Let's see. Go back to your screen there. You had v equals. Let me write that down. V equals 1/4 864x minus 2x squared. No.
Sorry.
2x cubed.
Mm-hmm.
864x minus 2x cubed. Okay, good. So I'll go back to my screen now. And let's see how we can check this a little bit on our calculator. So we're going to plug in our goal function into the calculator. But you can't plug in the original goal function that had both an x and a y, because your calculator can only work with one independent variable. So you have to plug in your simplified equation. I'm working this out on my screen on the calculator. You can follow along. So we got 1/4 times 864x minus 2x cubed. So we can't plug in the original goal. We can only plug in the goal after we've simplified. Actually, sorry, I made a mistake. Let's go back to your screen.
Okay.
Actually, your original goal function here was, let's see, v equals x squared times 864 minus 2x squared over 4x. X squared, 864 minus 2x squared over 4x. Okay, so now I'll go back to my screen. So it was x squared times 864 minus 2x squared over 4x. Now, before I enter this into the calculator, anytime you have more than one thing in your numerator, you have to put the numerator in parentheses, so the calculator will know it's all one thing. So I'll write in these parentheses. And anytime you have more than one thing in the denominator, you have to put the denominator in parentheses on the calculator to tell the calculator that that is all one thing.
Okay.
So when you have a complicated expression, it's good to write down the parentheses you'll need on paper so you don't get confused when you're plugging it into the calculator. So now let me try to carefully plug that in. So we've got x squared times, and now we have two parentheses in a row, parenthesis, parenthesis. 864 minus 2x squared. Now I have a right parenthesis, divided by, now I have a left parenthesis, 4x, and now I have parenthesis, parenthesis, two right parentheses. All right, I hope I got that right. All right, and are you putting that in your calculator?
Yeah, I tried it and it didn't work.
What do you mean that it didn't work?
Yeah, I guess I typed it in wrong. I have x squared times parentheses, parentheses, 864 minus 2x raised to 2, parentheses, divided by, parentheses, 4x, parentheses, parentheses. Weird, huh?
What do you mean when you say it didn't work?
Syntax error.
Oh, okay, well, compare what you have to what I have on my screen here.
Mm-hmm. X raised to 2 times, parentheses, parentheses, 864 minus 2x raised to 2, close parenthesis, divided by parentheses 4. I have the same thing.
Try getting rid of the two parentheses at the end because they're not really necessary.
Huh. Same problem. I'm not sure. Here, I'm trying to retype it real quick. X squared times parentheses 864 minus 2x squared close parentheses divided by this is 4x close. Huh. Yeah, now it works. I don't know.
Okay. Well, you could always go back in the video later and try to see. Oh, no, you don't have video of your calculator. Anyway, you can always. All right. So it's too bad we didn't see what was going wrong there. But anyway, this is the correct way to put it in. All right. So we go to the graph. Now, on my graph, I'm not seeing anything.
Right.
Because we have to adjust our window here. So we're going to get a volume here. We know that the maximum is actually going to occur. So I'm going to put in an x min of 0 because x has to be positive. And x max of maybe 15. It helps that we know the answer is 12, right?
Right.
Y min can be 0. And now we need a big y, well, y max I think maybe we could put in. Oh, okay. Now here's something that's confusing. Notice y here doesn't mean the same thing as in our notes.
Right.
This y is really v. This y is really v. Well, we know that the real answer is 12 times 12 times 12, right? So we'll put in v max 12 times 12 times 12, and then I'll add a little bit of extra buffer to give ourselves a little bit more space there. And now let's see what happens when we graph it.
Cool.
Now we can go to trace, and what number should I plug in for x?
12.
And you can see the cursor does appear to be here at the top, at the peak. And you could zoom in more to confirm that really is the max. Okay, so one advantage of this is if you can carefully type this in, this is a way to check that all that algebra that we did before, right? Remember we had to do a bunch of algebra before we could take this derivative? Right. So this is a way, you don't have to do that algebra when you type this into the calculator. So this is a way to make sure we got that algebra correct. Of course, the downside then is you have to be super careful to make sure you're entering it correctly into the calculator. So there's pluses and minuses there. But anyway, these problems can be checked. Notice that we just confirmed here that the graph really is concave down everywhere. It really is concave down everywhere. So this really is a global maximum. You can confirm that even more by shifting the window out further to the right. Okay, so if you have time during the test, you might want to try to use your calculator to check these. Although, as always, sometimes it's difficult when if you don't get the same answer in your calculator, it can be hard to tell if you made a paper mistake or a calculator mistake. But anyway, that's something you can practice to give yourself another tool. All right, so let's see. Moving on, what else do I want to mention on that? We fixed the units. Oh, one other thing. There was a point here where you had to do this calculation. I think you were trying to find y.
Right.
And you were having some trouble with that. So you probably broke it up into a bunch of steps. Let me just show you. How could you do this in one step on your calculator? The key is what we talked about. You have to put the numerator in parentheses to show the calculator that it's all one thing. And since there's more than one thing in the denominator, you have to put the denominator in parentheses. And the best thing is write the parentheses on your paper before you pull over the calculator. And so now I'll go to the regular menu here, and we can try this in the calculator. So it's left parenthesis, 864 minus 2. This parenthesis wasn't really necessary, but you had it written down, so I'll include it, times 12 squared, another parenthesis, divided by parenthesis. So it really helps to have the parentheses written down ahead of time, 12. And you actually don't need the closing parentheses at the end. The calculator could fill those in for you. It might be safer to leave those out. Did you try typing that in?
Yep.
And what did you get?
It's graphing. I'm going to go to Zoom
Standard. Oh, I'm sorry. I'm sorry. I didn't explain. This was a calculation that you did to find y. So this we should be typing in just our normal calculator window.
Oops.
Because after all, there's no variables here. So it's just going to graph it as a straight line, a horizontal line. So I meant to do this calculation just in your normal calculator window like I have here on my screen.
2. Okay. 864 minus 2. 12 squared. Close parentheses.
divided by 4. I get 12.
Okay. Now, I know most students actually prefer to not to do these in multiple steps on their calculator, and that's okay. But this problem, you're having some trouble with this one, so I thought I would show you here's how you could do it in one step by putting in the parentheses around the numerator and the denominator. But on the test, if you feel more comfortable doing things in separate steps, that's fine as long as you're getting the answer. Okay, so those are some points on that problem. Now, the key thing is the one thing that was giving us trouble was the end there when we were doing the second derivative test. Remember, here's our new second derivative test. We have to check that the second derivative is negative for all the x's in the domain. That's the way to prove that we have an absolute maximum. If the second derivative is negative for all the x's in the domain, that proves we have an absolute maximum, which is what we're looking for on these problems. Okay, good. Overall, that was a good process here, so let's go back to my screen. Let's see. So there's another problem that was kind of similar to this, problem 3 from the website. If we had more time, I would do that with you. But actually, since we're running out of time, maybe I would assign that would be a good homework problem to do problem 3 from the website. And of course, if you get stuck, your instructor has the explanations for all of these. I think at this point, even if you get stuck, if you just watch the instructor's explanation, you should be able to figure out what's going wrong. So instead of doing another problem like that, let me give you a different type of problem. So let's see here.
Yeah, I've seen on the test, like there's an option. You can either do this type of optimization problem or the type where you have to find some point. I don't like the other ones.
Right. Now, so the point is that your instructor is probably going to let you choose between two different types of questions. That's right. Now, they might not necessarily be the same types that you saw in the sample test.
Sure.
But anyway, you'll get to choose. So that gives us an edge here, since we won't have time to go over all the different types, but hopefully we'll have gone over one of the ones that your instructor is giving you the option for. One other thing that's just good to mention on that last problem, again, you can get a little bit more intuition for this by just thinking about the extremes. So notice this is a very practical problem. This is a problem like, say, if you're a manufacturer who makes containers, you'd want to make containers that had the greatest volume, right? So that you can store the most material in them without wasting any space. So this would be a practical problem for a manufacturer. So one thing the manufacturer might consider doing is they might consider having a tiny x. Okay, I was having a little trouble drawing that. But anyway, you might try having a tiny square base,
right?
To try to get the most volume. That way you have a really high height. But obviously you don't want to take that too far, because if x was 0, there would be 0 volume. And then another thing you could try is you could try having a huge base, which would leave hardly any material for the height. Just to do a quick sketch. But obviously, if the height was 0, then that would that would have 0 volume too. So clearly, the answer is somewhere in the middle. It turned out in this particular case that it turned out to be best to use a cube, which might be intuitive to you. The best way to do this was to have all 3 sides be the same length. But even if that was intuitive, the only way to prove that was by using our calculus here. Although I guess you don't really need calculus nowadays, because you can use a graphing calculator to work it out. So I kind of undercut my own argument. I was trying to show how valuable calculus is by the fact that you use it for these problems. But of course, you could just use the graphing calculator. Of course, it really helps on the graphing calculator to have a sense of where the answer is. So you can set your windows. The calculus was helpful to us there. Okay, so let's move on then to this. Let me write this down. Okay, so yeah, let's talk about that other type of problem. By the way, the problem that we just did was one of the problems from the sample test. So I think
Okay, cool.
that was a realistic type of problem. So how would we find the distance between these 2 points? Well, it turns out that we can use what's called the distance formula. Here's the distance formula. This formula is very easy to prove using the Pythagorean theorem, but we'll save it a minute and not prove it. We'll just memorize it. So here's the distance formula. Notice, what does this tell us to do? Basically, it just says subtract the... I got this wrong again. So those labels didn't make sense a second ago. I meant to use these labels. Okay. So all that we do to do the distance formula is we subtract the x-coordinates and square that. We subtract the y-coordinates and square those. We add them and take the square root.
Okay.
Excuse me, this just comes from the Pythagorean theorem. Okay, so that's an important concept for the next type of problem. Let's see.
Yeah, I saw my instructor do this for a second, and he said something about how you can just drop the square root sign and just continue on with the problem without it. I don't know if you're familiar with that or not, but he just kind of works out the problem without the square root, and then apparently you get the same answer.
Yeah, that's a good point. So we'll be talking about that. That's a good point. Okay, so here's the problem. So I think it's useful in these problems to start by drawing a graph. And clearly we have a line here, so let's graph the line. Now, we can't graph a line on our calculator unless we solve for y. So how would you solve this equation for y?
Y equals negative 6x plus 9.
And now we can pull over the calculator. I changed my window on the last problem, so I'll go back to Zoom Standard. Okay, now here's the line, and we want the point that's closest to negative 3, 1. Now you can't use trace here because negative 3, 1 is not on the function, but I think we can just move the cursor around to negative 3, 1. We can't
Yeah.
use trace because we're not on the function, but we can just move here. So we can go to as close to -3 as we can get and up to 1. Okay. So point with your finger. I can't see you doing this, but point to with your finger to the answer. What's the point on the line that's closest to this point? I'll give you a second to do that. Have you picked a point?
Yeah.
So I would say it looks like maybe around here, right?
Okay.
So I just want to make sure you understand the question. The question is asking, what's the point on this line that is closest to here?
Okay.
So just by eyeballing it, probably around here seems to be about right. Or maybe around here. All right, certainly not down here, say.
Right.
All right, so we could already start to eyeball it and say it's maybe around between 1.5 and 6 or something like that. Obviously, we can use calculus to get an exact answer. So I think this is a good step just to get some intuition for what the question's asking us for. We want the point on this line that's closest to where our cursor is here. Okay, we don't need to make up variables on this problem because we have natural variables x and y, and we need and this is already the constraint.
Okay.
The constraint is that we have to be on the line. Obviously, if we didn't have to be on the line, then the closest point would be x -3 and y = 1. So this is the constraint, and then we need a goal function. Well, remember, our goal is to minimize the distance. So the goal function would be that distance formula that we were talking about. Well, now we need to plug in for x1, y1 and x2, y2. Well, x1, y1 represents one of the points that we're trying to find the distance between. So what's one of the points that we're trying to find the distance between?
We have 1, -3. Sorry. Yeah. Yep, we have -3 and 1.
Good. That's one of our points. So we could plug in -3 for x1. We have to be careful with the negatives here. This is minus 3. And what could we plug in for y1?
1.
Good. And what do x2 and y2 represent then? x2 and y2 represent points on the line. x2 and y2 represent points on this line. Well, there's no need to keep writing the 2 anymore. We can just shift to x and y.
Okay.
The general distance formula uses subscripts of 1 and 2, but now we can shift to the variables we're using in this equation, which are x and y. So now we have our constraint function, and we have our goal function. Any ideas what we should do now?
Yep, we can, instead of having the squares in there, we can just expand and...
Yes. So we could certainly do that. There's something else that would be convenient to do first, however, which is, remember that we're not going to be able to solve as long as there's 2 different variables in here. So before we do anything else, how can we get rid of one of those variables?
Well, we can set the equation, well,
Right now we have an x and a y in our goal function, but we've seen on the earlier problems we're not going to be able to proceed until we get rid of one of those variables. So how can we do that? We can do it the same exact way we did it on the previous problems.
on the previous problems we were setting something equal to 0. Yeah, I'm not sure.
So what did we do on the previous problems to get rid of one of the variables? We used the constraint equation. On all the earlier problems, we used the constraint equation to solve for one of the variables, and then we substituted it into the other equation. All the earlier problems, we used the constraint equation to solve for one of the variables, and then we substituted that into the other equation. So that's what we're going to have to do here. Here's our constraint equation. We need to solve this for one of the variables and then substitute it into here. So which of these variables might be easier to solve for? X or Y?
Y.
In fact, we already did that when we graphed it. We
Right.
already solved it for Y to graph it. So what do I do now?
Now we can plug in the negative 6x plus 9 into y and our goal function.
Right.
And then now we can expand in the next step instead of using chain rule twice or 3 times.
Okay, good. So notice this really was the same method we used on the earlier problems. Why did we have more trouble seeing it here? It might be because you might not be comfortable thinking of this equation of the line as just being the constraint equation, but it really is. The equation of the line here is our constraint. The point has to be on the line, and then we just use the same method as earlier. So let's take this step by step. So what should I now write? What would be the next step?
You can write x plus 3. X plus 3, sorry, yeah. We can close out the parenthesis and have a new one, and then x
We
plus
have to
3
remember
again.
the square. Good.
Mhm. Well, would it be better to just write it out now, or should we keep it condensed? X plus
Well,
3.
I think the first thing we should do is simplify
Okay.
and then expand.
Okay, cool. So now we can write negative 6x plus 10 squared.
Okay.
Okay. And then now in the next line, we can expand x plus 3, x plus 3 again, minus negative 6x plus 10 times negative 6x plus 10.
Let's hold our horses here for 1 second. Okay, I wrote the distance formula correctly here, but I wrote it incorrectly here.
Uh-oh.
This should be a plus. Plus, plus, plus.
Okay.
And this should be a plus. That'll make the algebra a little bit easier. Okay. Good.
Cool. So now we can drop the square root. Or maybe,
I'm going to keep the square root in for
Okay.
a while.
Okay. So now we can take the derivative of, wait.
So the question is, what's the next step after writing down this line?
Right. So if we took the derivative now, we'd have to use product rule.
True.
So we want to avoid that. Okay. I'm not seeing what to do next. I guess I'm missing something.
Okay. Well, remember that we've already said that on this section, we're pretty much always going to be able to reduce the goal function to just a simple polynomial.
Mm-hmm.
So we expect that there should be some algebra that we can do that will allow us to reduce this to a simple polynomial. Why did you rewrite x plus 3 squared as x plus 3 times x plus 3? What was the advantage of that?
Okay, we can FOIL it.
Yeah, the whole point of doing this is so that now we can proceed with FOIL. Okay?
Okay.
So now what?
We can write x squared plus 6x plus 9 plus 36x squared minus
120x plus 100.
Now, do you see why I wanted to simplify before we did the FOIL? Because otherwise this would be, if we had done the FOIL at this point, we'd have all these unnecessary negative signs, and we'd have 3 terms here rather than just 2. So definitely we were better off here simplifying what was in the parentheses before we did the FOIL. Okay?
Okay. Now we can combine all of our like terms, and we'll have 37x squared minus 114x plus 109.
Okay, I hope you haven't made any mistakes. Those are some kind of unusual looking numbers, but hopefully we're on the right track here. Okay, so very good. All right, now this is about as simple as we can get. So now the next step would be to take the derivative of the goal function, because we want to see where this is. Do we want to maximize this or minimize it?
This one I believe we're trying to minimize, but I forget. Let's see. I don't have the title. Oh, yeah. Sorry,
remember we were talking about on our calculator how we were trying to find the point on this line that was closest to the cursor point here. So we're trying to minimize that distance. Okay? Now, if we proceeded here and took the derivative, this would still be kind of a complicated looking derivative. It wouldn't fulfill the promise I made you before. I was telling you that we were going to be able to just work with polynomials. So here we can use the trick that you had mentioned earlier that your instructor uses. The trick is just, would you agree that the way to maximize this function is to maximize this function? I'm sorry, the way to minimize this function is to minimize this function. Wherever this is minimized, this would be minimized too. That's all there is to the trick. So even though what we want to minimize is this function, all we have to actually do is minimize this function. I don't know what would be a good name for this function. I don't know. So maybe I'll call it, I don't have a good name for it, so I'll just call it Q. It's the quantity that we're trying to minimize. So the point is, if this is minimized, its square root will be minimized. After all, which is smaller? Square root of 16 or the square root of 4?
Square root of 4.
Notice the way to minimize the square root is to minimize the number inside of the square root. Which of these is smaller, square root of 9 or square root of 25?
The square root of 9.
Yeah, the way to minimize the square root is to minimize the number inside the square root. Which of these is smaller, the square root of 112 or the square root of 224?
The square root of 112.
Oh wait, how could you possibly know that? You didn't calculate the square root of 112 in your head, did you? Right? Well, you don't need to. Even without doing the calculation, you know that if the number inside the square root is smaller, the square root is smaller. So that's all. That's the whole trick that your instructor was using here. And that's a standard trick that we can use to simplify this. We can minimize the square root by just minimizing the number inside the square root. So now we'll minimize this function here. Okay, so what's the next step that we should take to try to minimize that function?
Now we take the first derivative.
Good.
We get 74. Yes, 74x minus 114. That's it.
Good. And then?
Okay, so now we need to set this first derivative to equal to 0. Right. I'm trying to think.
So we need to find the critical number, which is where the derivative is 0. That's right. Okay, so what do you get as the critical number?
Okay, so it's going to be 114 divided by 74. You get 1.54.
Okay, I hope we didn't make a mistake. But anyway, it approximates to approximately 1.54. Good. You could do this on your calculator, and you could get
1.54 is going to be...
So it's going to be 114. Sorry, you were saying? And then we can go to the math menu
Okay.
and change it into a fraction. 57/37. I don't know if that's any better. And I don't know if did you follow what I did. So this is how you can turn decimals into fractions. You go to the math menu, turn as fraction, and you can see that the exact answer is 57/37. Okay, so there's our answer. Now, what do we have to do next to prove that this is really an absolute maximum?
Well, we can take the second derivative, or we can do the integral test. Either or.
Actually, at this point, we kind of need the second derivative approach because those interval tests, the way we covered them, they only prove local minimums and maximums.
True.
There's a way you could adjust those so they would give you the absolute, but actually in this section, it's easier to focus on the second derivative.
Okay.
All of the problems in this section that your instructor is giving you, it's easiest to focus on the second derivative. So what do we get there?
So the second derivative is 74, which is positive. So that's not good. Wait, no, we're trying to minimize. That's right. Okay. So we're concave up. And yeah, so that proves that 1.54 is concave up. So it's a minimum.
Absolute minimum, yes. The key thing here is that 74 is always positive. If it was only positive at the critical number, that would only prove a local minimum. But since it's always positive, we know that the graph looks like this, and this is the absolute minimum because this is concave up everywhere. Okay, so this is the best approach for all the problems in this section. And your instructor always does this in their solutions. Your instructor always goes on and applies the second derivative test. So I think that's something they want us to do on the test. Okay, so now we haven't quite finished the problem. The problem was, what was the problem asking us for?
It's asking us to find the point in the line that's closest to the given point. So now we know that. So we found out the x value, and now we can plug it in to the constraint. So we can write down y equals -6 times, what was our answer? It was...
We can use this fraction to get to put the exact answer in, 57/37.
57/37. And then we can solve for y, and now we have a point. 6 times 57/37. So 18.24.
One moment. I got a different answer than you.
Huh.
So check how did you do that in your calculator?
Oh, I made a mistake. -6 times 57 divided by 37. That's -0.24.
Good. And we might as well change that into a fraction. So we go to the math menu and choose fraction. And what did you get? Did that work? Yeah.
It's -9/37.
I guess it didn't work. So does your calculator look kind of like this? Oh, my mistake. I screwed up. I didn't put in the negative sign.
That's the mistake I made. Yeah.
So, good. Math. And what answer did you get again?
That same answer.
-9/37. Let's check if this seems plausible. So we can go to our graph. And we can go to what x value?
We're going to go to 57 divided by 37. And then...
Oh, that doesn't match my prediction at all. All right, so that puts us here. And we wanted the point that was closest to -3, 1. Well, Maybe it really is closest. I think the x and y axes here are not the same size. It's kind of hard to eyeball this. So it wasn't. I thought the answer was going to be up here. So I guess the calculus saved me from my mistake.
It's hard to tell.
Close too. Okay. So unless we made a mistake, that's our answer to the question there. Good. Good.
Cool.
And again, you could check this on your calculator by typing in this whole function here and then seeing if that's really minimized in the right place. In fact, I'm not sure we got this right, so I'll go ahead and do that. So here was our function that we had. So we had the square root, and that puts in one set of parentheses. So one thing is, now we need an extra set of parentheses here to show where the square root ends and begins.
Okay.
So the calculator already put in the left parentheses. Now I need another parenthesis, x minus 3 squared plus -6. I'm going back to before we did the algebra so we can check if we got the algebra right. Squared. And then I need a right parenthesis to tell the calculator the square root is done.
It's 6x. 6x. I think. -6.
Thank you. My mistake. -6x. That would mess things up. Okay, good. Always important to double check. I'll go back to Zoom standard. So this is the distance function.
Mm-hmm.
This shows the distances. So now what point do we want to check by tracing?
We want to trace over to 5737.
Right.
57 divided by 37.
So fingers crossed.
Yep.
And that really is at the minimum. Excellent. Okay, so it looks like we got the right answer, and that really is the minimum here. Okay, very good. So again, it is possible to check these. You have to be very careful to enter it correctly on the calculator. That can be tricky, but if you're careful, you can check that you got those correct. Okay, where is the, well, let's try giving you a problem now. Let's try another problem from the sample test to finish out with. All right, so anyway, did that problem make sense?
Yep.
You said you found those problems more difficult than the earlier problems. The key is to see, ultimately, if you do look at them the right way, they're very similar. We still have a constraint equation, which is the equation of the line, and a goal equation. And then we use the constraint to substitute out one of the variables. Okay, so let me write this down. So here's the problem from the sample test. So let's try this on your screen. Oh. Okay, so let's try this.
Okay. I'm going to point a line as closest to the origin. Does the origin mean 0, 0?
There you go. Good.
Yeah. So okay. So now we need to use distance formula. can plug in this.
Okay, so we've made a mistake here. This should strike you as a little too easy. If you remember what we did in the previous problem, the algebra was much more complicated.
Mm-hmm.
Do you have the distance formula in your notes?
Ah. Okay.
I make that mistake a lot myself of leaving out those squares. So that's something to especially highlight. It's very easy to start forgetting to write in those squares. That's why the algebra here was turning out so much easier than the last problem that we did. That should have made us suspicious.
Well, this is easy. Okay. Okay, so I would still have this. I would still have this and this. And this would be good. One more. Ten x, 10x. 5. 5x squared. Okay, so okay. So we got 1 point. I can say so it should be. I'm gonna check this. Y equals 2x plus 5. And we're looking for the point that's closest to the origin, 0, 0. So we got -2, 1. Yeah, that makes sense to me.
So you tried graphing the original line.
Yep.
Let's see.
And then I guess I can double check.
And you said it looks like the origin might be the closest point. Yeah. Now you really can't quite eyeball these because the x-axis on your calculator has different units than the y. 1 unit on the y-axis is, you can see from the hash marks that 1 unit on the y-axis is longer than 1 unit 1 unit on the x-axis is longer than 1 unit on the y-axis. So it's a little hard to eyeball, but it seems roughly plausible that the origin is the right point. Okay, good.
And then I did the second derivative test just now. And the second derivative is positive at all. Like it's positive all the time.
Right.
So that's an absolute min. And then I guess if we really wanted the triple check, we could plug in. Well, I guess to be safe, you'd want to plug in right here.
Let's see. We'd want to plug in the first expression that was all x's.
So this one.
Yeah, let's go ahead and do that. Now, remember that you need to tell the calculator where the square root ends and begins. So you want to put in, there's going to be one extra set of parentheses. So you might want to draw those on your screen. One more left parenthesis at the beginning of the square root and one at the end. Although actually the calculator puts that left parenthesis in for you. But anyway.
Okay, so square root, parentheses again, x minus 0, close parentheses, squared, plus parentheses 2x plus 5 minus 0, closed, squared, and then one more. Okay, and graph. And we trace over to -2, and that should be our min, and it is. Cool.
Let's see, I'm having trouble. What did I do wrong here? Oh, okay.
Well, I guess this one might actually be easier than the other type of optimization problems where you have to use shapes and whatnot.
Once you know how to do it, it might be more straightforward. That's right. So what did you get as your answer?
-2, 1.
Okay, you were way ahead of me, but now I caught up with you. Yeah, that does look like the minimum on the graph. Good, so that looks like we got that one correct. Good. Let's go back to your screen there, and at the bottom, we should add one step. So do you see where you have d equals square root of 5x squared plus 20x plus 25? Then you said that you took the derivative of d, but you're really not taking the derivative of d. So you're taking the derivative of the inside. So we should define a new function. Let's call it, right in that space, let's call that q.
Okay.
Q equals 5x squared plus 20x plus 25. You can fit that in the space. Well, no. So that d is correct. And then maybe if you zoom in a little, you can just fit in between the lines you already have. Q equals 5x squared plus 20x plus 25, because the point is, if we find the place where the inside of the square root is minimized, we know that that will also minimize the square root. So then we found q prime, not d prime, because q prime was simpler, and we know it's going to lead us to the same answer. And you can scroll down and fix that at the very bottom. You can change your second derivative. You found that the second derivative of q was positive everywhere, but that also means that the second derivative of d would have been positive everywhere. Okay, I think that's a good method. So that was a problem. So now we did the two problems that were the choices on that sample test, and we saw how we could get both of those correct. I got one more problem from a sample test. Why don't we just do that last problem so that we're as prepared as we can be for the test? So let me write this problem down. But that was a good approach for that last question. That was a good way to do that, and it sounds like you're feeling more confident on those. So that's good. All right. Let me tell me when you have that written down.
Yep.
Let me point out something about the previous problem. Oh, or maybe not. I guess I didn't. Oh, I didn't write it down, but oh, here we go. So this problem that I took from the sample test, notice how your instructor says you must use calculus. So I guess there must be some way from just high school geometry to solve this as well. There's probably a way by like drawing a perpendicular. If you draw the perpendicular from the point to the line, that would also give you the closest point. So anyway, he's trying to make sure that there's no smart aleck in the class that uses high school geometry to get the answer. You must use calculus. I just wanted to point out why they were saying this. So if I was the instructor, I would give, and someone remembered their high school geometry, I would give them triple credit for that. I wouldn't penalize them for that. I'd be so impressed. But anyway, your instructor doesn't want you to use high school geometry to solve this. They want you to use calculus. I just wanted to point out that's why they're making those comments. So there's a similar comment on this problem from the sample test. Presumably there's ways to solve this using geometry without using calculus, but they want you to use calculus. I think that's the only thing that we would be considering anyway, but that's why they're saying that. Okay, so when you're ready, you can go ahead and try this on your screen.
Okay, it says to build a rectangle enclosure as shown. Is there something special about the picture?
Oh, geez, always complaints. I have to show you the picture too. All right, if you insist. All right, so yeah, that was my ungracious way of saying that I forgot to draw the picture. So here's the picture. Width and length.
Okay, cool.
So yeah, that is a key element of the problem. So you're right. So that was something that should be included, and now we're in better shape. Good.
Very cool. All right, so we have feet, and we have area is okay. So there's our length, there's our width, and this is W, that's W, that's L. Okay. So this length times width, and then we're trying to maximize the total area of enclosure. Okay. 2L plus 3W. 1, 2, 3. Okay. So I think we could solve for either here. Solve for 2L equals 1400 times 3W. So now, do this. So we drew the rectangle. We labeled our sides, length, width. Area is length times width, and then our constraint is 2L plus 3W equals 1400 feet. Okay, good. So now we want to do this, do 1/2. It's 1400 W is 3W squared.
change this to a fraction. Oh. All right. I think I did this correct. I'll just double check real quick. Got that. I plugged it in. I brought this over. I distributed the W, 400W, and it's 3W squared. I pulled out 1/2, and I have my constant and my polynomial. I have the derivative of the inside of this, and then 6W, 700, 3W. Set it. Okay, we're good. All right. Now, the length, 1400 minus 3 times 700 divided by 3 by 2. That cancels. I would check this in my calculator.
Good.
It's already, but 347, 350. Okay, so the question is, find the dimensions that will maximize the total area of the closure. Okay, so I think that's correct. Now I can take the second derivative, and that's just going to be -3, which is less than 0, which means concave down, which is absolute max.
Good. Now, the key thing that you might want to make a note of is that the second derivative is negative everywhere. Remember, if it was only negative at the critical point, it would only be a local max. But this second derivative is negative everywhere in the domain. That proves it's an absolute max. Good?
Okay, so that looks good. I guess I'll double check 2 ways. I'll double check, well, first, if I added 350 plus 350 is 700 plus, yeah, that's about right. Okay, and then I equals right here. Well, here. 3x, well, 1400 minus 3x. Let's put this with that 2 times x. And if we go over to some standard, which I'm gonna graph. I should graph. I'm trying to graph the area function.
Good.
And it's not working too well for me.
What's happening?
There's nothing on my window.
Right. That means that's because the numbers are too big to fit. So we need to go to our window menu and adjust. So what would be a good x min?
Like 500. Sorry, -500.
Well, x is a length, right?
Oh, 0.
So 0 would be a good place for that. And now, how big does our x max have to be to include, what's the x that we want to check?
We're trying to check 700 over 3.
So we might type in 700 divided by 3. That's 233. So to give ourselves some space, let's go up to 300, say, there.
Okay.
So that we can see the function on both sides. And then what would be a good y min?
Y min is also 0.
0. Good. And you can actually stop right here, hit graph, or actually all we have to do now is go to zoom. I'm doing this on my screen too if you want to follow along.
Mm-hmm.
You can go to zoom, and I hope this will work. Do you have an option for zoom fit?
I do. Yes.
So what that's supposed to do is if you choose the right x coordinates, it'll automatically choose the right y window. It'll automatically make the y's fit if you choose the right x's. So let's see if that works for us.
It does. Now I can trace over to 700 divided by 3. And it's hard for me. I'm looking for absolute max here. I need to zoom out a little bit more. Yeah. Yep. Good to go.
So what x value are you putting in?
700 divided by 3.
Right, 700 divided by 3. Oh, yeah, I guess it's kind of obscured by the equation, so you can't see it. But if you zoom out, and we try it. Oh, there we are at 700 divided by 3, and it looks like it's the max. And you can see this really is concave down everywhere, so that really is a global max. So yeah, sometimes these can be tricky to try in the calculator. The problem here is notice the y values are very large because this is the area of a field, right? Normally y only goes up to 10, but here the y's have to go up to what, like 81,000 or something. So a useful trick is to adjust the x's on your window and then okay, so let's see. Any issues there? You were asking whether it would be better to solve for L or for W. It doesn't make too much difference, but if you tried to solve for W, do you agree you'd have to have divided 1400 by 3? Mm-hmm. Or actually, maybe the way we solved it, maybe it doesn't actually make any difference at all. All right, in this case it makes no difference because we're just factoring the 1/2 out later on. So I guess in this case it didn't make any difference. It was good that you tried to decide who would be easier to solve for, but in this case it made no difference. By the way, you can see why we had to work on that algebra at the beginning of the session here, because here's where the algebra pays off, where it definitely helps to simplify the algebra before we take the derivative. So I think we made some good progress on that. You did that correctly. I noticed I didn't copy this, but your instructor specifically said here, include the correct units in your answer. So it is important. Remember there was an earlier problem where we put in the incorrect units, but here we got those correct. Notice, what would be the units for area?
Area would be feet squared.
But that's not what the question was asking for. It was asking for length and width, so those were really in feet. So it's good that you put those units in correctly. It looks like you do need that for full credit. Actually, in our answer, maybe we should put the width as both a fraction and a decimal. So let's write the width as a decimal too.
Okay. So 700 divided by 3. That means equivalent, I think, right? To something like that.
Yeah, or you can just say equals. Equals, okay. They're equal to each other. So it's 233.3. I think that's useful here because that way you can compare it to the length. So notice here that it turns out that you can now get a kind of a feel for how big the pasture, how big the fences should actually be by comparing those numbers. Again, this is a very practical type of situation that would be difficult to solve without the calculus, or at least without the graphing calculator. So that this is an application of the calculus. The key thing here is that you saw that the constraint was 2L plus 3W. We worked on those types of things yesterday because there's also a middle section. That's what they meant by the picture. That's why we needed the picture here. So this is a practical situation. I guess that this is a farmer who maybe wants to put pigs in the left-hand pasture and cattle in the right-hand pasture, and he doesn't want them mixed together. So he needs a section of the fence to divide those two, but he still wants to have the maximum space for the pigs and for the cattle. Okay, so I think that's good progress on that. I think you got through that without any help, so that looks like that would have been full credit. That was a real problem from one of the sample tests. Cool. These videos are offered on a pay-what-you-like basis. You can pay for the use of the videos at my website. There's a link to my website in the annotation. The address is www.freelance.com. algebra-teacher.com/videos.htm. Or you can just use the link in the annotation. Thank you.